This lecture focuses on machine learning. So in addition to this set of slides, there's a set of summary notes that has been uploaded to ClickUp. At the end of the lecture, I'll give you references for 2 books which you can find online. These are free books which you can use to supplement the notes and the slides. So if we ask the big question, what is machine learning and how does it differ from everything else that we've done? The main difference with machine learning is that it's able to learn, and as part of that learning process, it then produces some approach that can be used to solve the problem at hand. So whether that problem is a regression problem or a classification problem, the main aim behind machine learning is to learn from the data and then produce an approach that can be used on unseen data to solve the same problem. One aspect that we're going to look at in the lecture are different types of machine learning. So there's 3 main types. There are other types in addition to this, but these are the 3 that we're going to look at. The first is supervised learning, unsupervised learning, and reinforcement learning. The second part of the lecture is going to focus on different types of machine learning techniques. The aim of this part of the lecture is to give you an overview of the commonly used machine learning techniques. For the purposes of the course, we're then going to focus on a subset of these machine learning techniques. So we've already looked at evolutionary algorithms. We are going to look at neural networks next. We're then going to look at decision trees, and then to do some unsupervised learning, we're going to look at clustering, mainly using the k-means algorithm. So to move on to different types of learning. So the whole idea behind supervised learning is it will produce some type of approach that can be applied, and that approach is developed based on the data. 2 classical areas of supervised learning are regression and classification. So in regression, the idea is you're trying to find some pattern in the data. You've got some dependent variable which you're trying to find an approximation of, and you're trying to find the relationship between a number of independent variables and that dependent variable. Usually this relationship is presented in an equation or in some type of model. Classification is where you have a set of attributes. So for example, if you wanted to work out which type of flower a particular flower is, you may have information such as the petal shape, the petal color, the length of the petal, the width of the petal, and the classification of that instance of a flower will then be the type of flower. So the class could be a rose or a carnation or a lily, etc. So those are the 2 types of problems that are generally solved using supervised learning. When it comes to classification, your classification can be binary classification or it can be multi-class classification. In binary classification, you're either classifying something as belonging to the class or not belonging to the class. So for example, a particular instance of a flower is a rose or is not a rose. In multi-class classification, you have more than one class. So you may want to classify instances of flowers according to the different types of flowers. So either the instance is not a flower, or it is a rose, or it is a carnation, or it is a lily, or it is an orchid, for example. So that's the difference between binary classification and multi-class classification. The main thing that distinguishes supervised learning from the different types of learning is that it needs label data. So it will need a data set to learn from, and that data set is comprised of data instances. If you're looking at regression, the instances will be made up of values for the independent variables and what the expected output value is for the dependent variable. So we call that the output or the target value. So the main emphasis in terms of output for regression is the value of the dependent variable. For example, if we wanted to predict the mark that you'll get in the exam for COS 314, we could use your marks during the semester as independent variables. So your mark for assignment 1, assignment 2, assignment 3, and test 1 and test 2 would be the independent variables. We then try and find some model that maps that onto what your exam mark would be, and your exam mark will then be calculated using this model or equation. What we could use for training the supervised machine learning technique is data from previous year. So last year's COS 314 module, for example. All that would have to be the same are the independent variables, which would be the 3 assignment marks and the test marks. Classification, on the other hand, has in each instance a set of attributes and then what the corresponding class would be for that set of attributes. The label in this case is the class. In the regression example, the label is the actual target value for the dependent variable. So for example, if we go back to the flower example, each instance would have a value for the petal color, petal shape, petal length, petal width as attributes, and the corresponding flower that corresponds to that combination. So for example, rose, carnation, lily, etc. How is the data used in supervised learning? Essentially, the data that you get is divided into 3 sets. One is the training set, and that's the set that's actually used to produce the classifier or the regression model. The validation set is used to actually tune parameters for that particular machine learning technique that is used to produce the model. So for example, if you're dealing with the neural network, you'll be determining things like the weights. If you're dealing with the genetic algorithm, you're well aware of the parameters that come with the genetic algorithm, things like population size, number of generations, application rates, etc. And the last set is very important because this helps us decide whether our training has been done well enough, and that's testing. So the whole idea behind testing is to then take this model or this classifier that's been produced and apply it to data that has not been seen before to see how well it generalizes on that data. So that's the whole idea behind testing. So if you think about it, you'll see that how well your learning actually happens and how good that model is or that classifier is that's produced at the end of the learning process is very, very dependent on the original set of data. So when that data set is chosen at the beginning, your training set really needs to represent as much of that problem domain as possible to allow your classifier or your regression model that's produced to generalize well enough. So what do we mean by generalize well enough? It must be able to then be used with data that has not been trained on and still give you accurate results for that. So your data is very, very important in choosing the appropriate data. An alternative approach to just training and testing is something called k-fold cross-validation. So in k-fold cross-validation, the overall data set is divided into subsets or folds, and iteratively your machine learning technique learns on the set of folds. The way it works is on each iteration, the particular fold is used as a test set, and the remaining folds are combined to form your training set. So on each iteration, you have a different test set and a different combination of training sets. And this technique has been found to be quite effective when it comes to machine learning. So if we now look at unsupervised learning, it works in a similar way. It needs data to work, but the main difference is the data that's provided, there are no labels in the data. So you'd either have, when it comes to regression, you'd have the values for the independent variables. When it comes to classification, you'll have the values for the attributes. But in both those data sets, you will not have a target value, for example, in regression representing the dependent variable. And similarly, in classification, you won't have a value representing the class. So that's the main difference. There aren't any labels to learn from. So the algorithms that are generally used for unsupervised learning are grouping algorithms. So they group different instances together, and clustering is the most commonly used algorithm. So we're going to look at k-means later on. So clustering, what happens with that is instances that have some similarity are clustered together into different groups, and those groups could then correspond to your different entities. So for example, if we're looking at the flower example again, and we're doing, or we want to find out which flower a particular instance falls in, so we're now looking at a multi-class type problem where you have different types of flowers. What would happen in this case, the flowers will be clustered, or the instances of the different flowers will be clustered, and the idea is that each cluster will then correspond to a different type of flower. You can have some type of combination between supervised and unsupervised learning, and this is called semi-supervised learning. So in semi-supervised learning, basically what happens, some of your data is labeled and the rest of your data is not labeled. And then techniques are applied across the labeled and the unlabeled data in order to perform classification or regression. Type of learning, which we won't be looking at a lot in this module, and it's something you look at when you go on to honors, is reinforcement learning. This is very different from supervised and unsupervised learning. One of the main differences is that learning actually takes place while the problem is solved. So depending on the problem, the algorithms involved in solving the problem are seen as a set of agents, and the agents are solving this problem over a number of time steps, and the problem is solved in a particular environment. And what the reinforcement learning does is it reinforces the learning of the agents. That's the aim behind it. So these agents will perform different actions in this environment, and the actions are actually dependent on different stimuli from the environment, and the agents will then act accordingly. So depending on the performance of the agents in the previous time step, the agent will then be rewarded. And then going on to the next time step, depending on the reward and the performance assessment, the agent may be used or the agent may not be used. These agents can range from something like simple heuristics, to look at using different heuristics in a particular environment, to different algorithms, to different game playing strategies. So they've been used in a number of different domains. One where they've been very effective is in game playing, where you have a team of players playing and playing against each other in order to come up with the best strategy. So there's some competitiveness involved there. Okay. So that brings us to the end of the different types of learning. We've just covered the main 3 types of learning. There are other types of learning as well. The next section that we're going to look at is different machine learning techniques. The purpose of this section is just to give you an overview of the different machine learning techniques. Like I mentioned, some of these techniques we are going to look at in detail during the module. One of the techniques that we have looked at already is evolutionary algorithms. So the purpose of this is just to give you an overview, and we're going to go through the most commonly used machine learning techniques. So when you first start doing supervised learning and you look at machine learning, you look at classification, one of the first algorithms that you'll come across is the nearest neighbor algorithm. So this is used for both regression and is used for classification. And as its name suggests, the output that it produces in solving a problem depends on the neighbors of that particular data instance. So for example, in regression, you'll have a data instance and its neighbors will have certain values for the dependent variable. And for this particular instance of independent variable values, it will actually produce, for example, an average of the dependent values of the neighbors. Similarly, when it comes to classification, you'll find that the neighbors of a particular data instance that's in your data set, using the attribute values, you calculate those neighbors, and the ones that are the closest to it, you actually take the majority class from those instances that are closest already. So you may have 5 instances and 4 may indicate one class and 1 may indicate another class. So the actual class of that particular data instance will be what the 4 classes have indicated. Sorry, not the 4 classes, the 4 instances have indicated, the 4 nearest neighbors. So the k nearest neighbor is one of the most popular algorithms used when applying nearest neighbor algorithms. And basically what it does, it takes the k nearest neighbors, and based on the k nearest neighbors, it determines what the output is. So we've been speaking about determining the k nearest neighbors, and everything's dependent on the k nearest neighbors, but how do we actually work out what are the k nearest neighbors? So that will depend on the type of problem. So for example, if the values are continuous values that you're working with, then you can use the Euclidean distance. So the Euclidean distance between the independent variable values when it comes to regression, or the Euclidean distance applied to the attribute values when it comes to classification, and that can be used to work out the k nearest neighbors, so the smallest Euclidean distance. If you're dealing with discrete values, then you could use something like the Hamming distance. So those are 2 common measures for distance that are used when working out the neighbors in determining either the dependent variable value or the classification or class value for a particular data instance. Majority voting is something that's very interesting. That's used mainly in classification. So like I said, if you're dealing with a classification problem, you have a new data instance, you have attribute values for the data instance, and you want to work out which class should be linked to those attribute values. So for those attribute values, what class does the instance fall in? So you would use k nearest neighbor. You'll work out the k nearest neighbors. And like I mentioned just now, where you'd go with the majority class amongst those neighbors, that's what majority voting refers to. These are one of the most popular techniques used for supervised learning, specifically for classification. So the decision tree itself is a classifier, and there's some type of algorithm that will produce that decision tree for you. We'll speak about that a little bit more just now. So in your decision tree, the internal nodes represent the attributes to the problem. So for example, if you had an internal node or an attribute value being a petal shape, and the petal shape could be oblong, oval, or round, then that node will be able to take 3 children, one for each value of those attributes. So one for oval, one for oblong, and one for round. The leaf nodes represent the actual classes, and you can use decision trees to perform binary classification or multi-class classification. If you're performing binary classification, then the classes represent 0 and 1, where 0 means that the instance doesn't belong to the class, and 1 indicates that the instance does belong to the class. If you're performing multi-class classification, 0 means that the instance is not of that particular type, whether it's a flower or whether it's a type of vehicle. 1 will refer to the different types of that class. For example, 1 may be a rose, 2 may be a carnation, 3 may be a lily, for example. How do we get to these decision trees? So these decision trees are produced by induction algorithms. So the most common algorithm, or the first algorithm that was used to produce decision trees, is ID3. Another later algorithm is C4.5. You'll also see later on that you can use genetic programming to produce classifiers as well. So you get an idea of what a decision tree looks like. I'm going back to the same example of dealing with shapes and textures and things, but this time we're looking at fruit. So suppose you've got a golden delicious apple, you've got a grapefruit, and you've got a lemon. And you want a classifier where you've given attribute values can output whether the fruit is a golden delicious apple, a lemon, or a grapefruit. The attributes you have are the color, the shape of the fruit, and the texture of the fruit. Now we know all 3 are yellow, so whether you're looking at a golden delicious apple, a lemon, or a grapefruit, they're yellow in color. The shape, there's 2 values that the shape could take. It can be round or it can be oval. And the texture of the shape, the texture of the skin of the fruit can be either smooth or it can be rough. So if you look at the decision tree that was produced for this, like I said, each internal node, if you look at shape, if you look at texture, they represent an attribute. Shape can take 2 values. It can take round or it can take oval. So therefore, there will always be 2 children for the node shape. Similarly, texture can take 2 values. So the texture can either be smooth or the texture can be rough. You'll notice in this decision tree, color wasn't needed. And it makes sense because all the fruit are of the same color. So basically, if you look at the tree, it says if the shape is oval, then it must be 2. If the shape is, and that's the class that we're referring to, if the shape is round, then we need to look at the texture. If the texture is smooth, then it must be 1, which represents a golden delicious apple. But if the texture is rough, then it must be 3, which is a grapefruit, and 2 represents a lemon. So if it's round, we then look at the texture, but if it's oval, we know that the only fruit amongst the grapefruit, the lemon, and the golden delicious apple is the lemon. So we mentioned regression before, and regression is a type of a problem that's solved by machine learning. So the whole idea behind regression is trying to find patterns in data. And I'm just going to quickly remind you of the example we spoke about. So for example, if you wanted to predict what your exam mark is for COS 314, the dependent variable is your exam mark. The independent variables are the marks that you obtain throughout the semester. So your assignment 1 mark, your assignment 2 mark, your assignment 3 mark, your test 1 mark and your test 2 mark, those make up your independent variables. Those are the values we know, and we want to use the regression model to then predict your exam value. So what we do in this case is we'd use data from students from last year. We'd produce a regression model using that data, and then we'll use it to predict what the exam mark will be for students this year. So the whole idea behind regression is it finds a relationship between a set of independent variables and a dependent variable. There's 2 types, linear regression, so that's if you're dealing with some linear relationship. If your relationship is nonlinear, then we're looking at logistic regression. A measure used to assess how well your model is that's produced is something called the root mean square error, and that actually will map the distance or the difference between what the values your model is predicting and what the actual values are. So it gives you an idea of the quality of the regression model produced. Support vector machine. So the whole idea behind a support vector machine is it can actually produce something, and what it produces will either be a model or a classifier. So it's used to build classification regression models, and this model is built from the data. The one good thing that's very interesting about support vector models, support vector machines, is that they can produce both linear and nonlinear classifiers. So when we speak about nonlinear classification, we basically mean that you can have a set of attributes that's mapped onto more than one class. So far, when we've spoken about classification, we've basically said, okay, there's a list of attributes. What class does this combination of attributes indicate? Is it a rose? Is it a carnation, etc.? But there are some domains where you can have attributes that map onto more than one class, and that's referred to nonlinear classification. Support vector machines can also do unsupervised learning, and in order to achieve that, they do support vector clustering. Some of the techniques that have been employed by SVMs include things like subgradient descent, coordinate descent, least squares, etc. So this is one of the techniques that we're not going to go into too much of detail, but the main aim here is that you get an idea of what it's about and that it exists, and it's something that you can use if you want to use it in later years or when you go into industry. The next section that we're going to be looking at in the course is neural networks. And from our previous discussions on this, neural networks are essentially, as you know, a mathematical model of the brain that has been implemented to process things in parallel. And the 2 main things that it's very good at are pattern association and classification. So you could have a single layer neural network. So basically, what do you want from your neural network? You have some inputs and you want to produce some outputs. So with a single layer neural network, you basically have those 2 layers. You have the inputs, and they somehow map to your outputs. The way they map to your outputs is by taking a weighted sum of those inputs for each output node in your output layer, and then taking the sum and applying what we call an activation function to it. So if you can visualize it, you've got a set of inputs, and there's a node representing each of the inputs, and that forms your input layer. You then have a set of outputs, and there's a node in that output layer representing each of those outputs. And those inputs map onto each of the outputs by taking a weighted sum of those input values. If you're now looking at the multi-layer neural network, the multi-layer neural network has more than just the input layer and the output layer. There are hidden layers in between, and the hidden layers do additional processing. And you'll see later when we speak about convolutional neural networks, this is what makes convolutional neural networks different from your standard neural networks, is that it has a lot of layers in between there. You can have different types of neural networks, and we're going to look at this. You can have feed-forward neural networks. You can have recurrent neural networks that feed back values from the output back into the neural network again, or back into previous layers. And that's what you call a recurrent neural network, and we'll look at that. So we've spoken about weights, and weights are one of the most important things when you actually look at neural networks. The weights are what we do when we train a neural network. And usually in order to work out those weights, we apply different learning algorithms. So when it comes to neural networks, your classifier is actually the neural network. Or in terms of regression, the neural network will emulate that particular function. So your neural network gets trained like your previous neural networks. So supervised learning, they're usually trained on a training set. your previous machine learning techniques that we spoke about for supervised learning, they're trained on a training set in the same way your neural network is trained on a training set. But what happens during training? The main thing that's achieved during training are the weights of the neural network is actually determined. So if you have a multi-layer neural network, you need weights for each of the layers. There's usually a weight for each node in that layer. So you need to work out the weights, and learning algorithms are used to do that. Like I said, once you find a weighted sum of those weights, that weighted sum then produces the activation or the output for that neuron. So just to remember again, you have a number of layers. Each layer is made up of nodes. Those nodes represent neurons. And each of those neurons get input, and each of those neurons produce output. And the inputs and outputs go from one layer to the next until you eventually get to the output layer, which then produces output, and that's the output of the neural network. So when you take that weighted sum, different activation functions can be used to determine what the output of that neuron is. You can have something as simple as a binary function, or something more sophisticated as a sigmoid function. So the functions differ, and depending on the different applications you're using, you can actually work out which is the most appropriate activation function to use. And that's one of the aspects that you do when you design your neural network. Convolutional neural networks and deep learning. So they're an extension of the whole idea of neural networks. And the main reason or the main way in which they differ from your standard neural network is the number of layers that you have in between. You can have hundreds of layers in between, especially with deep learning neural networks. And we're going to look at that in more detail after we look at a general introduction to neural networks. So evolutionary algorithms, you're already familiar with this. We finished the section on evolutionary algorithms. And as you can see from the work that we've done on this, they can be used to solve optimization problems quite well. So how do they fit into machine learning and classification and regression? So actually producing a classifier or producing a regression model can be treated as an optimization problem. And the two algorithms that have been found to be really good at doing this are genetic algorithms and genetic programming. So the whole idea here is the genetic algorithm or genetic programming or the evolutionary algorithm is not the classifier and it's not the regression model. It actually produces the regression model, or it produces the classifier. This is very different from neural networks, where the neural network actually is the classifier. So when you design the neural network to do classification, you're actually designing the classifier. Similarly, when you're designing a neural network to emulate a particular function, that actually then performs the function. And this is where neural networks differ from evolutionary algorithms and machine learning. In machine learning, the machine learning technique is actually producing a classifier or a regression model. Common examples of classifiers produced by evolutionary algorithms include your standard rule-based classifiers, decision trees, arithmetic trees, and logical trees. When it comes to regression, so basically genetic programming has been proven to be very good for both classifiers and regression. It will basically produce a model or an equation for you that will specify the relationship between the independent variables and the dependent variables. This is quite an exciting idea, the whole idea of ensemble learning, and I find it very intriguing. So if you look at ensemble learning, the idea is we've been looking at single classifiers. So you either have a neural network to perform classification, or you have a genetic algorithm that will produce a decision tree that will perform classification. The idea behind ensemble learning is you actually work with an ensemble of classifiers or regression models. So that ensemble performs the classification or the regression. Ensembles essentially perform supervised learning. And each ensemble can be made up of different types of classifiers, different types of regression models, and that's where the design process now comes in, is in deciding which classifiers to include. As you have different classifiers or different regression models, each of them are going to produce a different output. And there must be some way in which you can combine that output to produce a single output, because although you're working with an ensemble, the output is going to provide is as if it's a single classifier or as if it's a single regression model. So it's going to produce not n outputs, it's going to produce just the one output. So there must be some way of combining the different outputs from each of the classifiers or models in the ensemble to produce a single output. And that's also one of the design aspects that you've got to look at when you're doing ensemble learning. A very simple type of ensemble is a random forest. So we spoke about decision trees. So a random forest is just a set of decision trees. So each decision tree will specify the class for that particular data instance that has been input to the ensemble. And again, majority voting is used. So if there are 10 decision trees in the random forest and 7 of them indicate a particular class, then in that case, the output of the ensemble will be that class indicated by the majority of the classifiers in the ensemble. Bagging is another popular technique that's used for ensembles. Again, you have a number of classifiers. They don't have to be the same type, and the idea then is again to take out the most prominent or the most common output from each of the classifiers and output that. Again, something like majority voting can be used. Boosting differs from bagging in that your ensemble is incrementally developed, and as each classifier or each regression model is added to this ensemble, it's actually trained as it's added, instead of working with an entire ensemble from scratch and training the entire ensemble. And that's the main difference. The main or most common ensemble technique that's used is something called AdaBoost for adaptive boosting. And although ensembles are not one of the areas that we're going to look at in the module, this is a very interesting area which you can use in either in industry if you join industry, or in your work if you're carrying on with honors. So, and you'll see more of this in your honors classes next year. The last technique that we're going to look at under the different types of machine learning techniques is clustering. What makes this special from the other techniques that we've spoken about is it's one of the main techniques used for unsupervised learning. So remember, with unsupervised learning, your data does not have labels. So for example, we don't know what the class is for a set of attributes. We don't know what the dependent value is for a set of independent values. And the idea is that you find some way of finding patterns in this data and the unlabeled data that can help you decide what the flower is, for example, or what the particular dependent variable value is. So we're going to look at this in more detail later on in the module. And the algorithm that we're going to look at is something called the k-means algorithm. And the way the k-means algorithm works, it decides that it's going to have k centroids. It chooses those centroids initially. And then as it gets new data from the data set, it actually finds a centroid that data is the closest to, and it adds it into a cluster with that centroid. So each centroid corresponds to a cluster, and as you work through your data set of unlabeled data, you add elements of that data set to the particular clusters depending on how close they are to that cluster. So how do we assess how close they are to this cluster? We work out how close the attribute values or the independent values are to the centroid of the cluster. And again, you can use distance measures like the Hamming distance or Euclidean distance depending on what data you're working with. The Euclidean distance is quite a common measure used for this. So if we look at a clustering example again, I'm going to go back to the example we looked at previously. You may want to cluster data that you have that specify information about flowers into different types of flowers. So for example, you may have details like the color of the petal, the width of the petal, the length of the petal, the shape of the petal, and you may want to find ways of grouping these together. So the idea is once you apply a clustering algorithm to this, like k-means, the different groups that you get out would actually correspond to different types of flowers. Okay, so that brings us to the end of the overview on machine learning. We are now going to look at neural networks in detail. That will be the next section, but we'll start that in the next lecture. As I mentioned previously, in addition to these slides, there are some notes that have been uploaded. They are summary notes, but in addition to those notes, you can actually use the following 2 books. These are free books which you can access online, and you can use them for additional reading if you want to, together with the notes and with the slides.